Good morning, everyone, or rather, good morning to the student who's watching. My name is Lucian, and I will be your tutor for today's Yeba Physics. Welcome to Yeba Physics for this lovely Friday afternoon. If you're watching this whenever in the future or right now, I have a student watching. If you have any questions, please ask, but we will be covering Snell's law today. Okay. So let me just get nicely situated. Okay, everything is streaming fine. Just want to check. Yes, my mic is broadcasting. So yes, should be fine. Let me just check my docs audio mixer. So yeah, it is picking up sound. Okay, so Snell's law. What is Snell's law? Okay, what does Snell's law state? Growing up in physics back in high school, this used to be my most favorite law. Well, this and the one on gravitation. Now, Snell's law simply states, let me just write it here. Snell's law. Let me just see if it shows up there. Okay, I need to write it somewhere here. Okay, so Snell's law simply states that if you have two media, let's say this is medium 1, this is medium 1, and this is medium 2. And each of these two mediums has a different refractive index. Say this one is N1 and this one is N2. Okay, these are two different media. Let's say this is one media and this is the other one, and they are one media, another media. They must be optically transparent. Light must be able to travel through them. Okay, now according to Snell's law, if you have these two media divided by a boundary, okay, and one media has a refractive index N1 and the other media has a refractive index of N2, and a light ray passes from one media into another media. Snell's law predicts that that other light ray will be, let's say this is the angle of incidence, theta 1, and this is the angle of refraction, theta 2. Snell's law states that if this light ray passes in from medium 1 with a refractive index of N1 at an incidence angle of theta 1, then the light ray will be refracted. Okay, it will be refracted, and that refraction, the angle of refractance, is equal, can be calculated using this law, which states that the refractive index of one medium times the sine of the angle of incidence is equal to the refractive index of the other medium or the second medium multiplied by the sine of the angle of refractance. Okay, this here in its simplest form is Snell's law. It's simple, beautiful, and it works. Okay, now what is a refractive index? Okay, now a refractive index is a dimensionless unit because it is a ratio between two speeds. The refractive index is the ratio between the speed of light in a vacuum. So N1 is equal to the speed of light in a vacuum divided by, let me rather just omit the ones. Refractive index is equal to the speed of light in a vacuum divided by the speed in the medium. So the speed in the medium. Now, if you notice, or you should know by now, if you're studying physics, that the speed of light is the absolute speed constant. Okay, so nothing can travel faster than the speed of light. That means whatever v you have here will always be lower than c. Okay, so taking that into account, n will always be bigger or equal to 0. It can only ever be equal to 1. Sorry, bigger or equal to 1. It can never be smaller than 1, because there is no medium in which light will travel faster than 3 times 10 to the 8 meters per second. Okay, so that is Snell's law in a nutcase. Now, Snell's law is easy, and the problems regarding Snell's law is also easy as well. Here we have problem number 17. Okay, before I continue with that problem, let me just see if everything is still broadcasting. Okay, still going good. So we have problem 17, which states a monochromatic, it means a single frequency, single wavelength, single frequency light ray in air. So we have a boundary, we have air on the side, and it enters a glass prism. Okay, this is the boundary of the glass prism. This is glass. Also, wait, I think I should put scenes. Now let me just check. Okay, that is me right there. I just need to move. Okay, I have moved my green screen. Okay, so we have light ray coming in from the air, a monochromatic light ray coming in from the air, moving to a glass prism. Right now, so we have a light ray coming in. This is, let's always draw a line horizontal. So this is what's happening. We have a light ray coming in, hitting the boundary. There we have the angle of incidence, theta I. Now, here's the wonderful thing. If the angle of refractance for medium 1 is bigger than the angle of refractance for medium 2, it will be bent towards that normal. Okay, if the angle of refractance, or rather if the second medium has an index of refraction higher than the first medium, it will be bent towards, or am I having it other way? Let me just check. Yeah, that's about right. Okay, so just forget the bending towards or whatever now. If we have this, and this monochromatic light ray coming in towards the boundary of the prism, the glass prism, the light ray gets refracted to some angle theta in the glass. Now they have some questions regarding this refraction. Okay, so they telling us in the glass prism. So we have this refraction going on. This is glass. This is air. We have a light ray, a monochromatic light ray coming in, and we have a refracted ray going out. This is the angle of incidence. That is the angle of refraction. Now, let's look at some stuff. Okay, sorry. There we go. The question asks, this monochromatic light ray is passing from air to glass with a higher refractive index. Check something. So, as we've said before, when light enters a medium with a higher refractive index, it is bent towards the normal. Think about it as what we always thought. Think about it as a, a car driving on a pavement on this side and grass on the other side. As soon as its wheels start touching grass, if it enters the grass at an angle and its wheels, let's say this is, I'm just going to, for simplicity, let's say this is the cart. Okay, this is grass. This is grass. Now, obviously, the grass will slow the wheels down. This is pavement. Okay, this car or this cart is moving there on the pavement. As soon as it starts hitting, this front wheel starts hitting grass, the front wheel is going to go slower, but that wheel is still going to go at its normal speed. So it's going to bend towards the normal. So that's how you can think of this. So whenever a light ray enters a medium with a higher index of refraction, the light is bent towards the normal. Okay, now back to our question. We have this single light ray. It passes from air to glass. Which of those statements are true regarding this movement from air to glass? Now, here's what you should know about refractive index. Refractive index is equal to the speed of light divided by the speed of light in that medium. Okay, because the speed of light is a different, the light has a different speed in that medium. Now, we know that c is constant, it does not change, but the speed of a light source can be written as frequency multiplied by the wavelength in that medium. But a very important concept is that the frequency in medium 1 is equal to the frequency in medium 2. So the frequency stays constant. Okay, now the speed changes. Okay, and if the frequency stays constant, the wavelength must change. The frequency is constant, so the wavelength must change. Therefore, refractive index is directly proportional to C over F will be a constant for both. So refractive index is inversely proportional to the speed in the wavelength in the medium. Okay, so the higher the refractive index, the lower the wavelength in that medium. Okay, because the frequency is constant. So let's see. I select 1. The wavelength is the same. No, the wavelength is not the same. We just established that the wavelength changes as it moves from one medium to another. The frequency is the same, but the wavelength is smaller than in air. The frequency is the same, yes, and the wavelength is smaller because the refractive index is higher, so the wavelength will be smaller. The frequency is the same, yes, but the wavelength is greater. No, the wavelength is not greater. Both frequency and wavelength are the same. They are not both the same. One has to change in order for the speed to change. Now, the wavelength is the same, but the frequency is greater. The wavelength is not the same. So let's check our answer. And yes, we are correct. The frequency stays the same, moving from one medium to another, but the wavelength changes. Now, depending on refractive index, the higher the refractive index, the lower the wavelength in that medium. Okay, I hope you guys understood that concept. Let me just check. Okay. Nicholas, Mr. Jansen van Vieren, did you get that? Okay. Good. So, question 18. Okay. The index of refraction for light, for red light in water is, and let's draw the situation. So we have, okay, I can change the colors here. Just before I do that, let's say we have, there's a red light in water and blue light. So we have air and then we have water are the two mediums. And we are given that the index of refraction, we know that for air it is 1, n equals 1 for air, and n equals 1,33 something, depending on the type of light that's entered. Okay, so for A, n is 1. Let's leave out the refractive indexes for now, or indices, we should say. So we have a red light coming in. We have red light coming in this beam. Is refracted. And the angle of incidence for red light is 83. Now, then we have for blue light, the exact same thing, but just the light is blue. Okay. Now I'm drawing these two separately, but they're actually both traveling at the same in white light, because white light is made up of both red and blue. So we have the blue light also entering at 83 from this white light, and then it's also bent towards the normal. So theta r, theta r2, theta r2 I should actually say, refractive, and this is theta r1, theta r1. Okay, so we need to calculate these two angles, theta r1 and theta r2, for blue light and for red light. Okay, so let's calculate it first for red light. For red light, we have the following: n1 sine theta incident plus n2 sine theta refracted. Okay, should make my r better. Refracted. Okay, now we know that n1 for air, because it's moving from air to water. Let me read the whole question. The index of refraction for red light in water is 1.331, and for blue light it's 1.340. So it's a minuscule difference. Now if a ray of white light, now white light contains both red and blue light, enters the water at an angle of incidence of 83 degrees, show that the underwater angles of refraction for blue and red is 47.79 degrees for blue and 48.2 for red. So for red we should get 48.2 degrees. Now, the incidence, the refractive index for A is 1, and the angle of incidence for A is sine 83 degrees, and that should be equal to the refractive index for red light, which is 1,331, and the sine of the angle of refractance for the red light. Now, if you were to work this out, you would say that 1 multiplied by the sine of 83 degrees over 1,331 is equal to the sine of theta, sine theta r, the refractive angle. Now, if you were to solve for theta r, now you can just punch that in your calculator. You will find that, let me see if I can do this on this Desmos calculator that's been given. Where's the calculator? Okay, there it is. Okay, so second function sine of logs, all that. Second function sine of 1 multiplied by the sine of 83, close the bracket, divided by 1,3331. There we have that this angle for red light, the refracted angle for red light, is 48.22 degrees on your computer. Okay, now let's go check. Is this what we should have gotten? Yes, indeed. We showed that the angle of refractance for red light is 48.22 degrees. So that is correct. Now for blue light, we need to show that the angle of refractance is for blue light, we need to show that the angle of reflected is 47.79. 47.79. So we have N1 times sine and the incidence angle equals N2 times the sine of the refracted angle. Then we have N1 is equal to 1. The sine of the angle is still the same. It stays the same. 83 degrees. And then N2 is 1,3. This is the difference. 1,340 for blue light. Sine of the refractive angle for blue light. Now, if you were to calculate the sine of theta r, it's equal to 1 times the sine of 83 degrees over 1,340. We have then that theta r, or the refractive angle, the angle of refraction, is equal to, let's put it in the calculator. Only thing that changes is this bottom part, 40 though. Let's see, enter. Oh, sorry, 40, so it's 47.79. 47.79 degrees is the angle of refraction. Let's check if that was supposed to be. Yes, 47.79 was indeed what we were supposed to get. So that is refraction. Now 19, question 19. A diver scratch paper. A diver shines a light up to the surface of a flat glass bottom boat at an angle of 30 degrees relative to the normal. Okay, so we have the water here. The diver is underneath the water. The diver is underneath the water. So we have, and he is shining light up to the surface of a flat glass bottom boat. So he's in water. This is glass, the glass boat here. A glass bottom boat. They should actually be on top of each other. Very close, or at least. And we have a glass bottom boat. Okay, and this diver shines light at an angle of 30 degrees. 30 degrees. If the angle of if the index of refraction for water and glass are 1.33, so this is water, it's 1.33. For glass, it's 1.5. Remember, now there are three media actually here. If you think about it. Okay, we have water, we have the glass, and then we have air. So three media. At what angle in degrees does the light leave the glass? So what angle of refraction occurs in air? So this is what's happening. It moves through the glass and out of the glass into the air. So in simpler version, this is what's occurring. It's moving at 30 degrees from water, which is an angle of an index of refraction of 1.33. So it's from water, 30 degrees. This is the water. It moves up to glass and then to air. Now we want this angle here. Now this is 1.5 and this is 1. So it will bend towards, let me just check it a new color. Once it's in glass, it bends towards there. So there we have a new horizontal. Let's pick a new color, blue. So it'll now bend again. So we want this angle here, theta refracted. Okay, so how do we go about calculating that angle? We do it step by step. First, we do it for these two materials. This angle here will become the incident angle for that one there. According to what do you call it? Alternating angles between parallel lines are equal. Okay, so for the first section, from water to glass, we have N1 sine theta incident equal to N2 sine theta refracted to the glass. This is for water and glass. Maybe I should make it here a W for water, angle of incidence for the water, and this is N2 glass. So the angle of the index of refraction for water is 1,33. The sine of 30 degrees. The angle of the index of refraction for glass is 1.5, and we need the sine theta r, so the angle of refraction. Okay, so angle of refraction will then be 1 comma r times the sine of 30 divided by 1.5 should equal the sine theta r, and that should be equal to, and then theta r should be equal to the inverse sine of 1,33 divided by 1.5 multiplied by the sine of 30 degrees. Okay, so the refracted angle is thus, let's work it out on the calculator. Okay, so we have, this should be 1.33, angle of incidence is 30, this is 1.5, so the angle of refraction in the glass is 26,3 26,32 degrees. Okay, now 26,32 degrees. Now this is what is happening. This is glass, this is water, and this is air. It's moving from glass so it's moving from glass, then it's moving to air. But now this is 30 degrees, and we've just established that this is 26 degrees. So this angle here, these two lines are parallel. These two normal lines are parallel, meaning this is 26 and that's 26.32. So the angle of refraction will be the next angle of incidence for between glass and air. Okay, so now for glass and air, this is for glass, the sine of theta incident angle, and then this is for air, sine theta refraction. So the incidence for glass is 1.5, the sine of the angle is 26, is the angle we just calculated, 26,32 multiplied by the index of refraction for air is 1. We have the sine of the angle of refraction. Now same steps, we do the whole same thing. Let me rather just, okay, so incidence sine of 1.5 times the sine of 26.32 over 1 would give me theta r. So theta r, the angle of refraction, let me just plug in here. This is now our new, that's 1, this is now 1.5, this is 26.32. So the angle of refraction is 41 when it leaves the glass, 41,68, or you can say 42, 41,68. Let's check if any of those answers. Now 41,68, there 41,68, and there it is. Let's check it. Yes, we are correct, it is indeed 41,68. So you can have Snell's law for hundreds of media, because the previous refracted angle become the new incident angle. Okay, due to just simple geometry. Now 20, problem number 20. A diver shines an underwater searchlight at the surface of a pond. Now the pond has a angle of incidence index of refraction of 1,33. At what angle relative to the surface will the light be totally reflected? Okay, now for total reflection to occur, you must go bigger than the critical angle. So first we will calculate the critical angle. Okay, the critical angle. And the critical angle occurs when the angle of refraction is equal to 90. Now in order to, this is N1 sine theta of the critical angle is equal to N of 2 times the sine of 90, because at the critical angle the refraction is 90 degrees from the normal. Now the sine of 90 is just 1, so N2 is equal to N1 times the sine of the critical angle. And we will be working out the critical angle. This is basically what they're asking. What's the critical angle? Because bigger than the critical angle, there will the light be totally reflected. It will not be refracted. It will be reflected like a mirror. So the sine of the critical angle is then equal to N2 over N1 . Note, for a critical angle, for some internal reflection to occur, the relationship between N2 and N1 is as follows. N2 must have a lower index of refraction. That's the only way this happens than N1, because it must be bent away from the normal. Okay, so the critical angle is then the inverse sine of N2 over N1. That's the critical angle. And in our case, it's the inverse sine of what is N2? N2 is the air, N1 is for water, 1,33. Let's see. So we have the inverse sine of 1 over 1,33. We have the critical angle at as 48. The critical angle is then 48,7. Critical angle 48,75 degrees. Now, for total internal reflection to occur, the angle of incidence must be bigger or equal to the angle, the critical angle. So the critical angle is 48,75. Did I do that correctly? I think I might have missed something. Let me see. Eight. I earlier got a different value here. I got a different value. Let me see. Can't be 48. Let me just check my math. Oh yeah, sorry. It's 1.3. Let me just check. The critical angle should be theta equal to the inverse sine of 1 divided by 1,33. Now, let me just calculate what is 1 divided by 1,33. Divided by 1,33.75. Inverse sine of 0.751. And 751. Let's see. 48. How come I got 48 and early on I got, when I calculated this, I got 41. The answer should be 41, but somehow I'm getting, this should be the answer, 41, 2. And I did get it earlier. The answer is, so the critical angle at least should be 41,8. I got it earlier on my calculator, but this is a difference now from what I get here on this calculator. Oh, here it is. I do get it. Oh, there's something different. Let's check. This value, the sine of that value, the sine of 41. Let me just check something. Erase that. The sine of 41, comma, which is what we should get, 41, comma 2. Now this, the sine of this angle multiplied by 1,33 should be equal to 1, but it isn't. Is it a surface of a pond? Oh, sorry, I switched these two up. This is a problem. Okay. So it goes from something at a high incidence angle to something with a lower incidence angle. At what angle relative to the surface? So I worked out that the angle, we worked out that the critical angle, we are correct. We worked out that the critical angle is, what was it? 48, comma something. Okay, we are correct. I neglected a certain part of it. So we worked out that the critical angle is 48,67 degrees. So that's the critical angle. Now, the critical angle is measured from the normal. Okay, let me just do this. That's the angle. There's the normal. We have the normal coming down. That's the boundary between these two. And then we have it at the critical angle of 48,67. So 48,67 is the critical angle here. Okay? But they want it relative to the surface of the pond. So they want it relative to the surface of the pond. Now, the relative to the surface of the pond means they want this angle. So all you do is you subtract this angle from 90 degrees. So the angle relative to the pond will be 90 degrees minus 48,67. Just a bit, should read my questions more carefully. So let's see. Erase this. Okay, so 90 degrees minus 48, rather 48,67, I believe, gives you 41,3. So this is the angle that they want relative to the surface of the pond, 41,3 degrees. And there we have it, 41,2. They got 41,2, we got 41,3. Okay, moving on. That's not a big difference. Okay, so question 21. A layer of water flows on carbon tetrachloride. So we have water on carbon tetrachloride. Let's call it short CTC. My chemistry is correct. Carbon tetrachloride, so it's carbon tetra 4 chloride, so carbon and 4 chlorines, I believe. I may be mistaken. I haven't done chemistry in a long time. Okay, so we have water and carbon tetrachloride. So a layer of water floats on carbon tetrachloride. The water has a refractive index of 1,333 and the carbon tetrachloride has a refractive index of 1,461, and they are in an aquarium. Okay, so to the nearest degree, what is the critical angle at the interface between the two liquids? Okay, so the critical angle between the interface of the two liquids. Okay, so the critical angle at the interface. So at this interface, the light ray must be parallel to the interface. So the light ray must be parallel to the interface. And in order for that, we need to calculate what is this critical angle here. Okay, what is that critical angle that will make the light ray parallel to that interface between the two liquids? Okay, so now we've already calculated critical angles before. We know that the critical angle is equal to the inverse sine of the refractive index of the second one divided by the refractive index of the first one. And in this case, it's the inverse, the sine inverse of 1,33 divided by 1,461. Remember, it must go from a medium with a higher refractive index to a medium with a lower refractive index for a critical angle to be calculated. So the inverse sine of this value, I'm not going to do it, so it's just 66 degrees. Okay, let's see if we do get 66. I've already done the calculation, but I will show you. Where is my critical angle calculation? I did one previously. Okay, so let's just do a new one. Inverse sine. Okay. Inverse sine of 1,33 divided by 1,461. 65.8 degrees, which is approximately 66 degrees. So 65.8 degrees, and there we have 66 degrees. We can check, and yes, it is correct. Moving on to question number 22. Then 23 will be the last one, and then we're done for today. Question 22. We have again, I think, if I remember correctly, yeah. the carbon tetrachloride problem. So an aquarium contains a 5 centimeter layer of water floating on top of the carbon tetrachloride. Okay. If the angle of incidence into the water from the carbon tetrachloride is 70 degrees, what is the angle of refraction into the air? So here we have water. This is in an aquarium. So we have water. This level is water. Here we have the aquarium with air. And here we have the carbon tetrachloride. So it moves from here so it moves from the carbon tetrachloride there, there. Okay, now first they tell us that if the angle of incidence into the water from the carbon tetrachloride is 20 degrees Celsius, we calculate this one, which will be the incidence angle for that one. It's like the previous problem we have. So this is for the between carbon tetrachloride and water, for between carbon tetrachloride and water. N1 sine theta 1 equals N2 sine theta 2. N1 is that of carbon tetrachloride, which is 1,461 times the sine of 20 degrees. N2 is for water, so it is 1,33 times the sine for water. The angle of refractance for water is what we want. Remember, this angle then becomes the incidence angle between water and air. So the angle of refractance then is equal to the sine. The angle of refractance is equal to 1,461 multiplied by the sine of 20 degrees divided by 1,333. It's a comma, sorry. Therefore, the angle of refractance will be, you work it out, you will get 22,02 degrees. That's the angle of refractance. And you can of course just work it out, just plug that into a calculator, you can get that. Now this angle here, this angle of refractance becomes the new angle of incidence between water and air. So 22, so now it's between air and water. So N1 sine theta 1 equals N2 sine theta 2. So N1, we have for water is 1,333. The incidence angle is the sine of what we just calculated, which is 22.02 degrees. N1 is 1,333 multiplied by the sine of 22.02 degrees equals, for air, angle of refractance is 1 normally, and we want this angle, the sine of the refracted angle. If you were to work it out, you would find, calculate it this way, 1,333 times the sine of 22.02 divided by 1 is the sine of theta r. So theta r, the refracted angle, if you work it out, is 30 degrees. 30 degrees. Let's check. You can do the calculations yourself. I've done them. Yes, it is indeed 30 degrees. Now for our last question. Question number 23. Let me go back to black rather. A person in a boat sees a fish in the water which has an index of reflection of 1,33. You are going to know the index of reflection of water off by heart after this. The light rays making up an angle of 40 degrees relative to the water surface. Okay, so a person in a boat sees a fish in the water. So here's the fish. Let me just draw a fish. So we have a fish. So there's a fish and a person in a boat here. And this person is, let's say, standing in this boat. And this person is looking at this fish. Now this person is looking at this fish. Person sees the fish. But it's not that, it's a bit exaggerated, but the person sees the fish like that. Now this person's, the light rays are making an angle of 40 degrees relative to the water surface. So this is 40, meaning the angle of incidence here, what we want is actually 50 degrees. So the angle of incidence is 50. We want this angle. This angle here, the angle it makes with the horizontal or whatever, whichever one is choose, but we just want the refracted angle. Let's see. So n1 sine theta 1 equal to n2 sine theta 2. Now n1 is the index of refraction of air, and the sine of the incident angle is 50 degrees. The index of refraction of water is 1,33 sine theta 2. We want theta 2. Okay, if you were to work it out, let's actually do this one together. So it will be the sine of 50 degrees multiplied by okay, let me just write it in the normal conventional way as it's written there. It'll be 1 times sine of 50 divided by 1,33. Now we want the inverse sine of that whole problem. It's 35 degrees. 35.17 degrees. So 35.17 degrees is the angle of refraction, but they want it most likely relative to the 35.17, so they want it most relative to the water surface. So we just subtract that from 90. So 90 minus 35.17, that gives you 54.83. So 54.83. Let's see, 54.83 is also 55. 54.83 is approximately 55. But also, yes, so indeed that is correct. And ladies and gentlemen, that is all that we have time for today. I hope you find some use or find some, not use, something in this session, and I will see you next week. All the best. Bye bye.